Hello everyone and welcome to today's online interview sessions. My name is Jia Huai and I will be your host today. And today we will be discussing the topic about hydrogen in the world of international transport management by exploring its key challenges and opportunities together. And hydrogen is often called the fuel of the future, but the big question here is how do we move it safely and affordably across the world? And to explore this, we actually choose a 2021 review article by Ratnakar and his colleagues titled Hydrogen Supply Chain and Challenges in Large-Scale Liquid Hydrogen Storage and Transportations. The article reviewed the supply chains, production, storage and delivery with a focus of liquid hydrogen, which is called LH2, and it's attractive because of its hydrogen high energy density and potential to reuse LNG infrastructure. But LH2 is not easy. It must be stored at minus 253 degrees Celsius, which creates boil-off losses, insulation issues, and safety risks. Current projects like NASA Cryogenics tanks and Japanese Hydra carriage are early step, but no commercial scale tanks exist yet. The author conclude LH3 could reshape global fuel trades, but only if cost, safety, technology barriers are all solved. And now, let us dive deeper, which our host Tu Wong will guide us into the main discussion.
Okay, thanks Jia Huai. The article is published in 2021 and it reviews the hydrogen supply chain with a focus on liquid hydrogen or LH2. It explains different production methods, including the thermal reforming, electrolysis, and the newer approaches like the photolytic and the biological processes. Among these, electrolysis powered by the renewable energy is seen as the most sustainable. For storage and delivery, the article compares compressed hydrogen and also carriers like the ammonia. LH2 is emphasized because of its high energy density and potential to reuse the LNG facility, which make it attractive for the global shipping. However, LH2 must be stored at minus 253 degrees Celsius, leading to the boil-off losses, insulation challenges, and the safety issues. Examples such as NASA cryogenic tanks and the Japan Hydra ship show progress, but no commercial scale tanks exist yet. In short, LH2 could support future clean energy trend, but only if its cost, safety, and technical barriers are addressed. Now, let's move on to the options such as liquid organic hydrogen carriers. And today, we are diving into one of the most exciting debates in renewable energy. How do we move clean hydrogen around the world? One of the most talked about solutions is liquid organic hydrogen carriers, or the LOCHS, to help us understand the promise and the challenges. We are joined by our guest, Chen Yong, a hydrogen energy specialist. Thank you for being here. Okay, for the agreement, many experts say LOHCS could be a game changer for renewable hydrogen transport. Do you agree they offer a safer and more practical solution than liquid fuel, hydrogen, or compressed gas?
I do agree, especially from a safety and infrastructure standpoint. LOHC stay liquid under normal conditions, which means that they can be handled like commercial fuels, whereby it makes them much less prone to hazards like high pressure leaks or extreme cryogenic conditions. And most importantly, we can use a lot of our existing fuel infrastructure, which can lower the initial cost. Okay, so for LOCH, it remains liquid under whereby it can just handle like no higher pressure risk, where they are safer than compressed hydrogen, which requires expensive gas, which is around $800 per kilogram hydrogen, or liquefied hydrogen, which uses 30% of its energy content just to stay cold.
And will you agree that this compatibility with existing oil-based infrastructure reduces the need for massive new investment?
Absolutely. You can store LOHC in regular tanks, whereby you can pump through to existing pipelines and use standard shipping vessel, which is big enough for advantage over liquefied hydrogen, which requires special cryogenic tanks. Imagine transporting hydrogen in the same ship that carry out state or storing it in standard tanks instead of building centralized cryogenic facilities. Projects like Germany's HISTOP have already proven that these cars transport cost up to 80% compared to liquefied hydrogen. However, there are several issues where the model performance will suffer if they incorporated straight into optimization strategy without first determining whether they could be used. For a point-to-point analysis based on Young and Overton's technique, this work extends the technologies under consideration and draws on the current data to investigate the application area of various hydrogen supply chain designs, which is used to fill a 700 bar compressed gas tank. It considers the entire supply chain, which includes the electrolysis of hydrogen, a large-scale storage to bridge the temporal gap between the supply and demand, and the transportation of filling spaces in facilities.
There are also some analysis also point out that the LOHCs can store hydrogen at ambient temperature, avoiding high refrigeration costs. Do you see this as a significant advantage?
Yes, I would see this as a significant advantage, whereby refrigeration for liquid hydrogen consumes a lot of energy, where both during production and during storage before shipping. Avoiding that is a big plus for LCS in terms of operational efficiency because when you store those in refrigerator, you might use it for industrial purposes.
Okay, thank you, Chen Yong. And now we are inviting our second guest, Elvis, for the disagreement.
That's a valid point. The extra chemical step to use energy. But if we can integrate waste heat into a dehydrogenation process, the loss can be reduced significantly. So, I would say it's a challenge, but not a deal breaker. Each time we load hydrogen into an LOHC, we go through hydrogenation. And to get it back out, we need dehydrogenation. Both states need quite a bit of energy. And without heat recovery, the efficiency can drop to around 60 to 70%, close to liquid hydrogen transport. But if we can waste heat from other processes, we can boost that up to around 80 or even 90%. So yes, it is a challenge, but it's not something we can improve.
Another viewpoint is that liquefied hydrogen, despite its cooling costs, might be more straightforward for the bulk shipping. Will you disagree?
I wouldn't partly disagree. Sure, once the infrastructure is built, liquefied hydrogen is simpler for bulk shipping, but that infrastructure is expensive. Hydrogenic tanks, especially pipelines, whereas LOHC can use that we already have. That makes it much easier for countries to start now instead for waiting year for a new facility.
And finally, some environmentalists worry about the safety or ecological risks of the LOHC chemical. Do you think those risks are manageable?
Yes, but it depends on the specific LOHC compound used. Some are more benign than others. With proper regulation, handling starter, and closed-loop recycling of the carrier liquid, the risks are manageable. But I think it's important we also look at unactive ammonia. For example, it's already shipping globally, but it's toxic if leaked. Methanol, especially green methanol, work for shipping fuel but still realize of sustainable CO2 sourcing. And electro fuel are promising, but they are still expensive and not industrial scale yet. So really, LOHC are good, but they are not only answer.
Thank you, our second guest, Elvis. And now we have discussed the pros and cons. And for this section, we're fortunate enough to invite one of the elite professional, Professor Liu, to share with us some knowledge in the topics. Thank you for attending this interview session, Professor Liu. And now I want to ask is, what recommendation would you give for scaling out LOHC transport?
Yeah, I am Professor Liu Wai-hin. Well, the first recommendation is for government to provide strong support for large-scale pilot projects. We have seen promising results from initiatives like Germany HYSDOC, but the next step is to scale up, involve multi-country in hydrogen's producer, maritime transport, and end user. This project allows us to identify operational challenges early, refine the technology, and give investors the confidence they need. Secondly, we should make better use of infrastructures that is already in place. LOHC can work with much of the existing energy transport network, so adapting current facility would be faster and more cost-effective than building new ones. This approach could also reduce the environmental impact of large construction projects. At the same time, it is important to have a clear international rules for LOHC safety, handling, and recycling. Having a consistent standard would make the trade smoother, lower risk, and give business and the public more confidence in the new technology.
Okay, and where do you see LOHC in the next decades?
In the next decades, I think LOHC will coexist with other hydrogen transport methods like liquefied hydrogen and ammonia, depending on system skill and use case. In the short term, like maybe over the next 5 years, there is like dominate in medium distance shipping routes, where existing infrastructures can be reused. In other words, if we solve efficiency challenges in hydrogenation and dehydrogenations, LOHC can play a central role in global hydrogen trade, connecting the renewable rich country to high demand region in the future.
Okay, now finally, here comes the final important question. What research areas are most urgent now?
Yeah, there are two. The first, I would say automation and AI optimization. Imagine a system where every step of LOHC transport, from routing at the export terminal to dehydrogenation at the destination, is monitored by sensor and fully managed by AI. That would allow real-time adjustment to pressure, temperature, and flow, making the process safer, more efficient, and less costly. Second, I will look into hybrid hydrogen supply chain. LOHC does not have to work alone. It can complement other carriers like ammonia that I said before, or liquefied hydrogens. For example, short distance routes might use LOHC for flexibility, while long distance bus shipment could rely on ammonia. Research into how this method can be integrated could make the global hydrogen network more resilient and adaptable.
Thank you for our guests sharing and our professional recommendations. And now we have explored all the key points from the chosen article on the hydrogen supply chain and the challenges of large-scale LH2 storage and their transports. And from just now to here, and we have summarized all the article, highlight all the agreements, and arise all the concerns and share the recommendation together. And the takeaway is very clear. Hydrogen could reshape the global trades, but LH2 face many serious problems in cost, safety, and technology. And overcoming this will require a lot of engineering, innovation, policy supports, and international cooperations. These make the article directly relevant to international transport management because if LH2 becomes viable, it could transform all the port infrastructures, shipping routes, and supply chain worldwide. And that's all from us. Thanks for watching these interview sessions, and we hope that this gives you an insight into both the opportunity and challenges of hydrogen transport, and lastly of why it matters for the future of global trades. Thank you very much.